Hi, now let's move on to LSTM recurring neural networks and variance thereof. So as a recap, our RNN, our main RNN equation is the one that describes the state at the time step t, and the same state variable, but a step one time step before, so t minus 1. So as we saw, this equation yields a gradient update, which is quite sensitive to vanishing gradients. Specifically, when our chain multiplications involve matrices, Jacobian matrices with small spectral norm, smaller than 1, then we will have vanishing gradients. Now, what is the key idea of LSTMs? How do we transition from RNNs to LSTMs? Here is a graphical illustration of how an RNN looks like, of the computational graph of an RNN. So the key idea here is that if we were to set somehow, to make sure somehow that our Jacobian of our current state with respect to the previous state would be roughly 1, then we would have no vanishing or exploding gradients, right? And this is quite evident from here. So if this guy is approximately 1, there is no vanishing or exploding gradients. So then the idea or the way that we can achieve that is to remove the immediate, the direct nonlinear relation between st and st minus 1, right? So here in this equation, st and st minus 1 are connected by this hyperbolic tangent, and because this hyperbolic tangent has often gradient values smaller than 1, that can cause problems. If we were to replace this nonlinearity with an identity, we wouldn't have these problems. Also, to avoid continuous overriding of states, we would like to modulate here the input variable, the previous state variable, as well as the output variable. These are the key ideas that, according to which we can we can transform an RNN to an LSTM. So let's go about this step by step. So how to make an LSTM. Let's say we start with our RNN equations here. We want to drop the nonlinearity because the nonlinearity returns gradients that are smaller than 1, right? So by doing that, our state at time step t is equal to this intermediate, let's call it memory variable gt. Now, as we see, these two guys do not have any nonlinearity, right? So there is no nonlinearity in our neural network, which is obviously bad. This means that basically all our transformations can be reduced to a single matrix multiplication. So what if we add the nonlinearity? However, instead of adding it between the state variable, instead of adding the nonlinearity in the equation that connects the state variable with itself from the previous step, what if we add the nonlinearity on the memory variable, right? So the memory variable here has now the hyperbolic tangent. Let me make this a bit more clear. Now the hyperbolic tangent is in the memory variable, which enters our state variable via addition. However, our state variable between two subsequent time steps is not changed from a nonlinearity per se. And now the next step is how are we going to now we have no vanishing gradient in that sense, so we are not going to have contributions smaller than 1 contributions to the gradient of our state variable with respect to itself from the previous time steps. However, we have also no way to modulate the inputs, the outputs, and the previous times. The previous states, right? So, is the previous state always important? Probably not, right? So we want a way to automatically figure out when or to what degree we should trust our inputs, our previous states, and our outputs. We can do this by adding gate variables. So the gate variables here are f of t, I of t, and I of t, which are basically a sigmoid of the transformed input. However, what is the problem again with this formulation is that still the output variable plays no role, right? So this is not desirable because, for instance, when we want to do translation or when we want to do text generation, our previous outputs from a previous time step should play a role for the next generation, right? Like a sentence is literally depending on previous outputs. So what we do then simply is that we add one more gate, an output gate, and then we create an output variable mt, which takes the transformed version of our state and modulates it by the output gate. By putting all these things together, we've got an LSTM. This is it. So we can break actually down an LSTM in intuitive steps. There are two key components. First, we have to make sure that we've got no vanishing gradients, or at least we reduce the chances of vanishing gradients, especially for longer time steps. And two, we want to modulate our inputs, outputs, and previous memory states, because our future predictions are not, they should take into account to what extent the input, output, and previous memory states are important. Graphically, these equations here, so I've got them here also. Graphically, all these equations here can be represented by this computational graph. Now, this looks a bit complex, but we can go now step by step and see that it's actually simpler than it looks. So let's say that I am, the LSTM, and now I'm going to see how I will do the forward propagation. So first, as an LSTM, I have to determine how much trust, how important my input is. This means that I have to figure out figure out the value that my input gate will return. So this is from this equation, and this would correspond to this guy here. So basically here and here. So first I compute how much I trust my input. So I see new input, like I'm the LSTM, I see new input. How much is this input relevant for my next step? For instance, if it's a comma, it's not very relevant. I can move on. Or if it's like a sort of useless word in terms of text generation. Okay, after I figure this out, then I want to know how important is my previous state. So now, moving on from the input to the previous state. For this, I have to, basically I call this a forget state. So shall I forget my previous state, or shall I keep it? So this is this guy, this equation here. And in the computational graph, this is found here. So this is my second step. Okay, now I know, or at least I have derived how important my input is and how important my previous state is. Next, I want to figure out what could be a relevant new memory for my model. So this is described by this equation here. So a potential new memory. And this in the computational graph is computed, from this pathway. So as we see, we're having we compute these parallel lines one by one. Now I have created a new potential memory. I might use it, I might not use it. That's the point, I need to first compute what could be a nice memory, potential memory to update my state, and then see how much I trust it now. Now I can compute my state. And how do I compute my state? Well, basically I am using this equation here for my new state variable. So to do this, I need to now I need to first modulate my new potential memory from g of t here with my input. So my new memory g of t is a vector, and my input gate will tell per dimension. So note here, these are element-wise multiplications. Will tell me per dimension which dimension is relevant and which dimension is not relevant for my inputs. For my new memory. After I take my previous memory state here, which I multiply with the forget state. So forget gate. So per dimension, I'm deciding, okay, this dimension for my previous state I should keep, and this dimension I should not keep. Okay, assuming for instance 0 or 1 value for the sake of simplicity, right? And now I combine these two factors together, here and here. So I add them together, right? I add how much I've forgotten from my previous state together with how much of my new memory I should pass on. So I add all this together, and then I arrive at my new state. And then I need to decide for my new state, is it actually relevant for my output? So it could be that my new state is quite characteristic of what my LSTM has seen so far, but it's not super important for returning an output, a particular output. So to do this, I combine here and here my output to obtain my new output variable. Note that the output variable m of t is different than the output gate O. And now this m of t is passed along to the next time step. Right, here I broke actually into two parts. Right, so okay, now I described it in twice. So your new output is here, right? But it doesn't matter. Now you get the idea. So some LSTM insights. Comparing the state equations between the recurrent neural networks and the LSTMs, we observe quite some differences here. The LSTM has a nonlinear relation, right? So it's not like we have dropped our nonlinearity. However, if we focus on the state variables, there is no direct nonlinearity involved. So this means that we will encourage strong gradients, or at least there is one pathway that will contribute strong gradients to our model. The fact that we have a nonlinearity is critical, right? Without a nonlinearity, then we wouldn't be able to actually capture anything really interesting. What is also quite different is that we are using these sigmoids here via the forget input and output gates. We use these sigmoids to squash values. So basically to state how important our intermediate internal variables are. This is very different from an RNN, because the RNN just projects these internal variables to the member state without really making a distinction. Now, unrolling the LSTMs is basically the same thing as, well, conceptually, that is, like for standard recurrent neural networks. So the internal equations are a bit more complicated, but the idea is actually very similar. Because of the linear relation now between the state variable over time, the vanishing gradients are mitigated, and LSTM captures short-term as well as long-term correlations. Therefore, right, like the vanishing gradient doesn't sort of push away the long-term components of for the forward and the backward computations. Now, LSTM has been a particularly successful model out there. Various variants have been proposed. For instance, LSTMs with pip-hole connections, so adding more connections within your computational graph. Gates who have access to all previous cell states, not only the memories. Bidirectional recurrent neural networks, GRUs, phased LSTMs, skip LSTMs. So basically, much has been researched there. Feel free to read more if you're interested. Thank you.